So today we're going to be looking at digital signatures, and we're going to code Rust to create a digital signature, and then we will verify it. So first thing we will do is import k256 crate and rand to generate a random number. The three functions are to generate a key pair, so we'll generate a public key and a private key. We'll sign the message with the private key, and then we'll verify the signature by checking it with the original message and the public key. Right, this is the code which does work. So I'll just demo that and then we'll actually look at it in more detail. So you can see it's comparing a good message. So the good message is the original message that was signed, and then I'm passing a bad message. So it's actually using the public key, but against a message which has been tampered with. So the output of the function is false because the message is not the same as the message which was originally signed. So a key thing to think of here, which again I'm not teaching here. I'm trying to I'm trying to explain what I've learned. Digital signatures, when they're used with Bitcoin, Satoshi used DER, Distinguished Encoding Rules, and they were already defined, and they were supported in the OpenSSL library. Basically, it's a way of serializing the signature, because I didn't know this, but with a digital signature, there's two components. So you need to serialize them, just put all of that into the signature, and you need to do it in a structured way. So you've actually got these here, which are the marker, the length of the signature. You've got something called an R value and an S value. If you want to know more about those, there's a good site which is called Practical Cryptography for Developers, and it's beyond my level, but there's the R and S of the signature. So the signature actually returns R and S. So when you come to verify a signature, you need to effectively deserialize it and then use these two to come to value. So let's go and look at the code again. And I'll open it with Vim because it's probably easier to read because it hasn't got all the type hints. So we're using signing key, verifying key with our generate pair. So the signing key becomes effectively the private key. The verifying key, just rewind. The signing key, so that's using a random number. So the random number creates the signing key, which is more commonly known as the private key. The public key is derived from your private key. It's like a jigsaw puzzle. The two pieces fit together. So you get back a tuple, private key, public key. Once you've generated those, you can then sign a message using the signing key, which is using the private key. So you use your private key with a message. That function returns a U8 vector, and the signature, so it's 256 bytes. When you sign it, you have to tell Rust that the message is as underscore bytes. Now, I thought it would be bytes anyway, because even when it's text, it's still bytes under the hood. But the sign function needs to have the message explicitly declared as bytes, and the same here as well. So this is where we serialize it with the DER, which we just looked at. So signature to DER, that's where we're serializing it. Again, here we need to be explicit and say as bytes. And then that becomes a vector, or effectively it's an array, ends up as an array. They're treated the same. And that's then what gets used when we go to verify. So the signature can be passed around in public, obviously, and so can the public key, and so can the message. The only thing that you don't want to send around in the wild is the private key. So the private key only ever gets used up here to generate the key pair and to sign the message. So it's used here and here, but it's not ever used for verifying. That's the whole beauty of it. You don't ever need the private key to be able to verify a digital signature. So further down, we've in main, this is where we actually use these functions. So we're basically deconstructing the function there. So generate key pair is returning a tuple. So we've got the private key, the public key, which are the output of this generate key pair function. From that, we also we actually then create a message, which is hello object_sig. So the whole purpose of this is to actually try and understand a bit more about object_sig, which is arguably the most important operator in Bitcoin script. Bitcoin script is what is used by the nodes when they validate a transaction. And as long as 51% of the nodes validate it or invalidate the transaction, then all is good. So the message, that's the good message. That's the message that we sign. So we pass in the message. We pass the message in here into our sign message function. And we're sending in a reference to the private key because we are going to be needing the... Actually, I think that's just to keep it like the others. Yeah, so it's a slice. Then we print the signature. And then I've created a bad message. So that's so that I can show both cases. So using the same signature and the same public key, we get a invalid message because the bad message is effectively equivalent to a transaction, say a Bitcoin transaction, where the contents of the message were changed. So just because you've got a signature and a public key doesn't mean the actual contents are valid. So if we just run it again, I'll clear the screen. So that's the actual serialized signature, which is the DER signature. So that represents some of those values which were on the web page. So this is from the Jimmy Song Programming Bitcoin book. But yeah, so there you can see how it's serialized. You've got a marker, 30 and 45. So 30, 45. Marker for the R value. And so these will be different. And then, so you've got the R length, the R value, marker for the... There's some Python code as well if you want to try that out. So yeah, using the good message, we actually established that, the bad message gives us false and the good message gives us true. What do I mean by the good message? The good message is the message which we signed. Where did we sign it? Here. So that's what we originally signed. That's why it validates to true. This bad message, we never actually signed it. All we're doing here is checking if it's valid. We didn't actually sign it. So that's a quick look at Rust, K256 crate, rand, RNGS, OSRNG to create a random number. Don't try and create your own. Random numbers apparently are incredibly hard to create randomly, believe it or not. As bytes, so that's probably worth just remembering in future. You may or may not have to be explicit about declaring things as bytes. The DER signature, that is quite specific to Bitcoin. What else did we do? We deconstructed a function which returned a tuple. And we converted that signature as bytes into a vector, which is basically similar to an array. And so when we actually passed it into the next function, it actually appears as ampersand square brackets U8. That does confuse me with the Rust, that you're using a vec, but it looks like an array when you come to use it in a function. So there we go. Hope that's at least sparked some interest. Even if you're not interested in Bitcoin, then we have just looked at digital signatures. And I did also create this web page on my website, Red and Green. It's not a shameless plug. I will actually show you something useful. I've talked about it in a couple of other videos, but let me just demo it again. This is a Python Streamlit thing that I built. So you've got your private key, which is generated by your code, and you've got your public key. So hello Rust, and then so this is our message. As soon as I hit enter, it will get signed with the private key. So the message is being signed with the private key. So now it's been signed. Now it's been signed, we've got a signature. And now we can verify that signature with the public key. And that public key is valid because that public key is the corresponding or the associated public key which goes with the private key. So any other public key would, if one digit of that had been different, and also if you tamper with the message, just change one character, it completely alters the signature. So yeah, thanks for watching. And elliptic curve signatures, practical cryptography for developers, DER, you can read about it in the Jimmy Song Programming Bitcoin book. And the Rust code, I'll probably put this as a gist on my GitHub page, and then I'll put a link to it in the video description. So yeah, there you go. Hope that's been useful, or even if it's not useful now, you might remember it in the future. So yeah, thanks for watching. Thumbs up, subscribe, and all that. Thank you.